Okay, so we are super lucky today to have Shaz Qadeer visiting us from across the lake. Friend of the group, has done all kinds of incredible work on model checking. Long career, super high H-index. But today we're going to learn about this system they built, P, which is useful for writing all sorts of event-driven systems. So thanks, Shaz.
Okay, thanks, Zach. Okay, it's great to be here. It's been a long time since I stepped on the UW campus, and I had almost forgotten how beautiful it is. And I was reminded of that as I was walking towards this building through that, the fountain area, and I saw Mount Rainier in the backdrop. And you guys work in an amazing place, so congratulations to all of you. And so I will tell you about this project on the programming language P. So I have only one motherhood and apple pie slide, and after that I will dive right into my stuff. So this slide is basically saying this is something revolution that people in the software industry are wrestling with, Microsoft in particular, where I work. So that Microsoft increasingly it is clear that we're not going to make that much money out of shrink-wrap software, right? And the world is moving towards devices and services, and all the software that glues devices that are embedded in our environment, in our homes, in our offices, and services that run on the data center. That software that glues all that together is increasingly relevant to the software industry and to Microsoft in particular. So I think that the work that I'm doing with P attacks some of the pain points in writing that software. So if you look at device drivers and system software that powers cloud services, it's complicated for a variety of reasons. But in this talk, the focus of this talk is on the problems of concurrency, reactivity, and failure. So what do I mean by that? So it is very common in this kind of software that you have multiple processes running concurrently and communicating with each other using either shared memory or via message passing. This is a classic challenge. People have been wrestling with how to build correct concurrent systems for decades. Another thing that these kinds of programs have to deal with is this issue of reactivity. By that, what I mean is that in non-reactive programs, I'll give it by contrast. In non-reactive programs, input arrives. The next input is not going to arrive until that input has been processed. Okay, so it's assumed that there's some queuing of inputs going on. That is not possible in a lot of these kind of systems. That kind of queuing will have too much performance overhead. So while one particular task, one particular work item has been processed, the system has to be ready to take in other work items. So that makes invariance complicated. Okay. Complicating all that is this issue of failures. So in a lot of software we write, if a failure happens, then you can just shut down the software and you can reboot. That would be unacceptable in many of these situations. So even in the presence of failures, partial failures, the service has to continue. So something reasonable has to happen. So that adds yet another source of complexity. So what happens as a result of all these complications is what I call Heisenbugs. So this is a riff on the Heisenberg uncertainty principle, which I learned when I was in high school and in college. So the idea with these bugs is that they are not reproducible easily. To reproduce these kinds of bugs, you have to observe the system, and the act of observing the software system fixes this bug. So fixes it in the sense that the causes of the bug are not under the direct control of the programmer. So when you try to observe the system, it inadvertently changes those things that cause the bug to happen in the first place. The classic example of this is a concurrency bug. So if a particular interleaving between multiple threads running on a CPU caused a bug to happen, when you start inserting breakpoints or you insert logging code, that influences the scheduler behavior, and now that interleaving might not show up. So this is very unpleasant.
One concrete example that I think everybody's seen recently. So for those of you in 505, if you run cock IDE in the debugger, it's fine. If you run it normally, it'll crash constantly. So it gets stable in the debugger.
I
So
see.
you can't find why it's crashing because all of a sudden it's stable.
Yes, yes. So yeah, and it gets even worse. So in distributed systems, for example, the processes that are causing such a Heisenbug might be running physically distributed, one in this data center, one in that data center. So often, by the time a crash like this happens, you can't repro it, so you start looking at logs, and that turns into its own cottage industry about how to make sense of these kinds of logs that are millions of entries long and so on. So this is an enormous impediment to programmer productivity and software quality. Here's a concrete example of a Heisenbug in a distributed storage system. So this is, so in Azure Storage, this particular software is quote unquote the next version of Azure Storage. It was being developed in collaboration with some of my colleagues in MSR and Azure engineers. So as with all these kinds of systems, you have this notion of data items. Data items in this parlance are called extents, okay? So at the top level, the metadata is partitioned among extent managers. Each extent manager is responsible for some partition of the extents. And each datum has to be replicated for availability. So the service wants to make sure that there's a certain minimum number of replicas of each extent done at any point in time. So if a particular extent node fails, right, then the system has to bring up another extent node and add some of the copies, move some of the copies over there. Okay? So Cheng, who is my colleague at MSR, he believes in rigorous testing and software engineering and whatnot. So he wrote unit tests, and all the unit tests are passing. That's great. Then he has integration tests, right? So these integration tests, they launch one extent manager and a few nodes, and they kill an extent node and make sure that the extents are repaired, and that's also working. So all the unit tests and integration tests are working, but stress tests fail from time to time. And he didn't know why they are failing. The manifestation of the stress test failure is that at some point, one node is brought down artificially. Of course, this is a stress test. But that failure is not getting repaired. The repair gets stuck. Okay? So it is one of those classic things where when the logs have accumulated and they're very long, and we don't know how to fix that. And by the way, this is not just a Microsoft-specific problem. If you look at the logs of open source distributed systems, they're filled with reports of Heisenbugs. So our goal is to find and fix Heisenbugs during development and testing. We don't want to go through this painful process of debugging these kinds of things in production. So P is an attack at this problem. Here's the rough workflow that a P programmer uses. So the P program is a repository of code, model specifications, and unit tests. The P compiler takes that program and it can emit C code, right, on the right side for execution. So the C code is going to work with foreign code, native C code, right, because the entire application is not expected to be written in P. So some of the application that's not related to concurrency or protocol management would be written in native C. So the generated C and the handwritten C are compiled together with the P runtime library, right? And that runs as the application. The main novelty in P is this other path here. Yeah.
Or just with the handwritten and generated code?
Yeah.
Do they call into each other, or is the handwritten always called from the generated C, or?
No, they can call into each other. Okay. Yeah, that's right. Yeah. So one of the things that you have to do in P, key design feature in P is I'm not actually going to cover it, is that it has this explicit foreign code interface, both for calling into P program and also for P to call out. And there are some kind of mechanism there, and the programmers have to adhere to it, especially with the protocol for passing values in and out, who owns what and stuff like that. Okay. So on this other side, what the P compiler does is it generates a collection of unit tests. But these unit tests are interesting. They are concurrency unit tests. So inside the unit test, in fact, many different processes are created. and they are going to interact with each other, sending messages to each other. And along all the executions that are implicit in that multi-process set of executions, some specifications are checked. So this is what I call concurrency unit tests. The distinguishing feature about these tests is that all the sources of non-determinism are controllable, and in fact, as accessible to this systematic concurrency testing tool that comes with P. So what this means is that these sources of non-determinism can be enumerated algorithmically using various kinds of search heuristics. And you get, if you find an error, you have a perfect repro because you can just replay those choices. So typically, we expect that the programmer does iteration over here for a while before the code gets deployed. And hopefully you get catch a lot of corner cases earlier. My personal experience is that the kind of bugs that you find like this within minutes are the kinds of things, exactly the kinds of things that will manifest over months or years in real systems. But you catch them very quickly here. Yeah.
Is this both for multi-threading and multi-process applications?
No. So the execution model, I'll go into that later. It's a pure message passing. It's not shared memory.
Okay, so pure message passing.
Yeah.
And is this like chess, the systematic tool?
Yes. What you can think of this capability is the chess-like capability, what you're getting over here. Yeah. The main difference because you know about chess, the main new thing, the main innovation here is that in chess, there was no way for modeling the environment in which your component is running. So that was basically, that didn't scale, because what that meant is that because you can't model, that means that any kind of non-determinism over the environment now you can't use. Yeah. Yeah. Okay. So a comment about modeling and programming. So this may not be an issue to people in this room, but whenever I present all this to, there's this community of people called the formal methods community, right? And they work on modeling languages a lot. So there's this issue about how is this different from blah, 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 blah modeling language, which does model checking or something like that, right? So I think that the key difference is that a lot of modeling languages, they are separate from code. And in fact, the connection between the model and the code is not formal, and it's left unchecked. You're left to your own devices. There are a lot of, there's an insane amount of work trying to bridge that gap by doing all sorts of model extraction. We are not doing any of that. What we are doing is we are just using straightforward compilation techniques. So what we are, P is both a modeling language and a programming language. So what is getting tested is exactly what is getting modeled. So it blurs the distinction between modeling and programming. Where you are modeling is in the part where you're modeling the rest of the system. So when you have a software component, right, it's interacting with the hardware, it's interacting with the network. Well, the network is not a piece of software, right? It has failures happening in it. So those are the things that you model also as a P program. So in a P program, there's code that gets compiled to an executable, and then there's the part of the code that gets erased because it models some physical entities or models systems that are outside the part that you're programming with P. Does it make sense? Okay. All right. So I've been pushing on this for a while in Microsoft, and we got some successes. Most notably in the driver space, device driver space. So since Windows 8.1 time, the USB device drivers that have been shipped with Windows have been built using P. And many of those engineers have gone on to work on other projects, and they're taking some of these ideas and encouraging other engineers in Windows to do that kind of stuff, to program in this way. We had an interesting experience with HoloLens also. In HoloLens, it's not Windows-based. It's some kind of a commodity, custom OS thing. So they didn't actually use a generated code, but they modeled a firmware protocol, a DMA protocol using P, and then the execution model that they were using in the actual driver was similar. The programmer hand translated P code into the executable code. And we're also getting some traction. Yeah,
So in that case, would you consider the use of P modeling more like TLA plus?
that's right. Correct. But I think it's still slightly better. If I were to hand translate,
Plus cal code or something.
plus cal code would, I think, be closer because it is still imperative. But if you had a TLA plus specification and you were hand translating it into this kind of event-driven coding, it's more like you're more likely to make mistake, right? Because you are making a direct jump from a purely logical specification to something that is highly imperative. The programming model in P, I have not got into that, but it's very similar. It's basically event-driven programming. So you write event handlers, you have states, right? So it already looks like that. I'm more willing to trust that you may not make a mistake. I mean, you can still make mistakes, and of course you'll make mistakes, but it's still better, I think. Okay, so P has its own syntax. It's a separate language, and it works with an explicit foreign code interface with C, with native C. It's hosted in C. So we have one other approach to providing the same kind of programming capabilities, but implemented as an extension to an existing language, to C#. So that's what we call PSharp. So unlike P, where you're programming with an explicit foreign code interface, here the host language is C#. So you have the event handling glue, and within those, with those events, the handlers, you just write native C# code, right? So it's a much more integrated experience, and you can continue to use your existing IDEs, existing debuggers, and so on and so forth for debugging the code. So it's very nice. Another very important feature, advantage of PSharp over P is that it can be used to find and reproduce Heisenbugs in existing code. Why is that? Because the existing code is, let's say, is written in C#. Well, what you can do is you can do with a little bit of refactoring of existing code. What you can do is you can do all the networking related plumbing, model that in something that looks like P#, while leaving the event handlers in native C#. And then you can start using P# for testing all that. So in fact, the data loss bug that I showed you in Xtor vNext was found and reproduced using P#. That was already code that was written in C#. But by doing modeling around the handlers that were written in C#, and by writing specifications that P# provides, you're able to test existing code. So as you can imagine, it's a little bit reduces the barrier to entry for potential users. Yeah.
So could I just write my program in C and not have any special libraries, and then just have like an interpreter for C or something that lets me tweak all the non-determinism that the operating system would usually control?
So
What do you mean?
that is, I would say that. So I know why you're asking. You're asking that because then the programmer doesn't have to learn some foreign syntax and semantics, and they can continue to live in this familiar world of C, right? However, I think that's easier said than done. Here's why. C has this model. The model of sharing in C is not clear, right? Remember, we're talking about concurrent programs here.
Yeah.
So the typical thing people do when they want to do concurrent programming with C is that they extend C with threads, P threads or something like that.
Mm-hmm.
So that means that potentially every heap access that you do is a point of communication.
Yeah.
So modeling that and doing the testing with that kind of semantics is very expensive. If you don't do that and you have some kind of a protocol for sharing, like based around locks, well, now if you have to now express your intention regarding that protocol in C, you have already put a foot into something that is not quite C, right? And from there, it's a slippery slope of changing the language more and more, right?
It's also probably hard to verify that you actually stay within your framework, right? That you don't access memory on some other.
That's correct, yes. And if you add various sorts of specification mechanisms to that, it's not C anymore. It is C with some other specification mechanism floating around in it. Yeah.
Can you contrast P with, say, the Java Pathfinder, where it's not C, but which unlike C actually has slightly better defined semantics and it's pretty easy to interpret the bytecode?
No, I think it's the same thing because it's basically for multi-threaded Java.
Yeah, exactly.
It has all the same problems with shared memory concurrency.
So
Yes.
on shared field access, they conservatively assume, I mean, they have some points to analysis or since they're operating on a live heap, they can do points to analysis to see if it's a shared field or not, but they have to conservatively
Yeah, so,
break and possibly do
yeah. When I show you more details about P later, you would see that a closer. Well, okay, I think that the reason you are talking about Java Pathfinder is because of the systematic testing capability, right?
Exactly.
I see. So there's 2 points of comparison. Whether these kinds of testing capabilities are present in another language. And the second thing is that what is this language, which existing language is this language most similar to? So the programming model that P has, it's not similar to multi-thread programming, not at all. If anything, it's closest to actor-style programming. So what is a common example of, like Erlang, for example, right? Or something that is very popular in modeling the state charts thing. Those would be the closest analogies from a language standpoint. From the point of view of testing, I would say, like chess or Java Pathfinder, those kinds of things are there. Yeah. Right. So P and PSharp are all available open source. Before I get into the details of P, I want to mention one other interesting thing that happened. So this tussle between a new language and a library extension is real, and I have really come to deeply appreciate this. So there is this engineer in Office Core Platform. He came and talked to us, and he really likes P, but he didn't want to take a dependence on P because he didn't want to work with a foreign code interface. And plus, he would have to take a dependence on my compiler, right? And who knows, who are these NSR guys floating around, or can we really trust them? They seem to be playing with the different kinds of rules. So what he did was he went ahead and based on the open source implementation of P, he did a library extension to C++ with providing basically the same set of features that P provides. But it is all very nicely integrated because the C++, the standard C++ compiler understands all that stuff. And he re-implemented his own runtime library because it's very nicely integrated and so on. So I mean, these are the kinds of, so if you want quick impact, I think designing new languages is not the right way to go. Okay, so a word about now I'm going to tell you a little bit about what P looks like. Okay, so it's what is known as state machine programming or actor-style programming. So this is basically a dynamically created state machine. It's called artifact manager machine, and it will have some data inside it. It's like a class with some fields inside it, right? And it will have an input queue. So somebody else in the environment can send a message to it, which is an event and a payload. That gets put into the queue at the tail of the queue. And then, somebody else can send a message. Okay, then that gets put at the tail of the queue, right? And then this guy starts executing. So all these machines are running concurrently. And it will be in one of these macro states. There are 2 states here, init state and reconciling. And then dequeues a message from the head of the queue, either the head of the queue. Actually, it's not quite head of the queue because you have this defer annotation in a state. So if you defer a particular event, and that event happens to be at the head of the queue, then it will be skipped over. So it's not strictly first in, first out processing. But once a message is dequeued, then you find the appropriate handler for it. Let's say the message was eStart. Then it says that the handler for it is, hey, just go to reconciling and go wait there or do something over there. So then it changes the state and so on. And maybe then it dequeues M prime. And then this one happens to be eQuery artifacts complete. Then it executes this handler whose code I'm not showing you. And perhaps that handler sends out 2 other messages to some other machines or actors. Okay, yeah.
So why did you decide to have defer and not do FIFO processing? Is that for priority reasons in device drivers or?
Yeah, so this is a very interesting question. So the semantics of P regarding dequeuing events is that the event at the head of the queue will always be dequeued, whether you have a handler installed for it or not. So this is because we wanted to make P responsive. So if you forgot to handle some event, then you will be immediately reminded of it because an event will be dequeued, you don't have a handler for it, and the semantics is that an exception will be thrown. So this is it's like a tough cross to bear because now you have to, in every state, you have to basically deal with the possibility of dequeuing any event that your protocol is allowing, right? Sometimes that is too arduous, right? It can cause too much state blow-up, or it can cause too much complication in your code. So sometimes if you know that you are blocking on an event E that you expect to arrive soon, in that case, you can choose to not handle F, G, and H, and you can defer them in the state until E arrives, and it's not going to cause a loss in performance. So that lack of responsiveness is okay, right? So the idea is that the defer annotation should be used sparingly, and every place where you're using it, you need to really think about it whether that loss of responsiveness that is going to be entailed as a user using that defer annotation is worth your while. Yeah, that's the idea. Okay, so then we can go look at how the code of inside a machine is structured. So at the top level, you have three kinds of entries. You have fields, right? And you have states, and then you have functions. Okay? So fields look like this. So you have variables. So we provide primitive types like Boolean, bool, and int. We also have types like sequences and maps. And we have tuples, and then you can have type synonyms also. So some of these names are type synonyms declared elsewhere. It's a statically typed language. Then you can have states. You've already seen a few states. One thing I want to point out here is that if you look at the state reconciling, the handler for eUpdate artifact manager is written like this. It's like an anonymous lambda, right? Which takes a parameter. So this parameter here gets bound to the payload that accompanied this event when it was sent from the sender side, right? And then you can have functions also. So this is useful for code factoring. So an important aspect of P is that function calls, everything is passed by value. So you cannot have aliasing, and you cannot have low-level data races by definition, right? So it's a pure message passing thing. But of course, as a result, there's a lot of copying going on in the system right now. And one of the things that I'm currently wrestling with is, the same kind of things that, things like linear type system or better kinds of memory management guided by type-level annotations that will reduce the amount of copying that I'm doing while still preserving the data race freedom guarantees. Okay. Okay, so specifying asynchronous systems. So I already talked about the unhandled event exception. Well, there's an illegal cast exception also. That's not particularly interesting in your assertions. The most interesting things are that you can specify general safety and liveness properties. This is very useful for, especially for distributed systems. So I want to show you, so I have some explanation here for safety and liveness. I don't think it's necessary for this audience. Everybody knows what safety and liveness are? Okay. So this is how you write specifications in P. So they're written as monitors. We don't have any temporal logic and whatnot. You just write monitors, executable code. So monitors have this kind of pub/sub thing going on. So every monitor subscribes to some events, right? And whenever those events are sent by anybody in the system, if a monitor has subscribed to that event, that gets funneled to this monitor. And then the monitor provides handlers for updating its local state in response to those events. So this way you can actually write global assertions. You can write assertions about correlated state between different parts of the system. So this one is basically checking that you cannot have more than 3 ping events for whatever reason. Okay, yeah.
So monitors can't read the state of other
Correct.
actors, but they can always just keep a ghost copy of the state.
That's right. So whatever state you wanted to keep track of, ship it to it.
Yeah.
Yep. Okay. So that is safety. Liveness is a little bit more involved because liveness is a specification over infinite executions. So to specify liveness, we have annotations on states, hot and cold annotations. So you have hot states, cold states, and just normal states without any annotation. And the analogy is that of temperature. So the temperature of an execution starts at 0, and if the temperature stays in a hot state for a step, its temperature increases by a little bit. Okay? And we never want the temperature to reach infinity. If it reaches infinity, then that means that there's a bug. So if it stays, and by the way, I forgot that when it enters a cold state, the temperature is reset to 0. Okay? So if you stay in a hot state for a long time, right, and your temperature keeps going up, so you eventually have to get out of the hot state, right? And then so basically this is the specification, right? And we have ways of testing for violations of that. This is pretty general. For those of you who are into automata theory and omega automata over infinite strings, this is equivalent to Rabin acceptance conditions. That means that this is general enough to capture pretty much anything of interest. Yeah.
Do you need to make, so how does this work? I guess that there's no assumption about distributions of inputs or anything. This is for any possible input stream. I see.
Yeah.
And so because there's no failure or asynchrony, you don't have to worry about.
I think I know what you're asking. It's about fairness constraints.
Yeah.
So I'm hiding that. So the issue is that imagine I generate an infinite execution by starving a particular process.
Yeah.
That's not cool, right?
No.
That's not legal, right? You can always create bogus error conditions, right? So all this business that I'm talking about is modulo fairness constraints. So fairness constraints enter P executions from two places. First of all the P machines that are constructed, they have to be fairly scheduled. That's just baked in for any of this. Second thing is that there's a modeling construct in P called non-deterministic choice. In P, it's written as $. So in P, you can say if $, right? And this evaluates to both true and false non-deterministically. Then we also have a $, more expensive $. This is fair non-deterministic choice. So what that means is that it cannot, after a certain point, keep evaluating to true or keep evaluating to false. It must keep flipping. But it's okay if it evaluates to true 1 trillion times and only then evaluates to false 1. So it's fair in the infinite sense, not fair in the random sense. Okay. All right. So we treat this testing problem as a search problem. Okay? So this is probably not a surprise to people who are who have read the model checking literature. That's classical contribution of the model checking community. So what this means is that your system is viewed as basically a graph, a directed graph. So you start in a state, right? And then you have transitions coming out of that state, and those states have transitions going out of them. And an execution is some path through this graph, and you have a specification, and then you run the monitor along any such execution, and you check that specification, right? Whatever safety or liveness thingy. So the question is, this is, as you can imagine, this can get very large. If the branching factor of this graph is k, then after depth n, you can have what? K to the power n. So the number of possibilities increases exponentially with the depth to which you go, right? This is not good. This is not good. So not surprisingly, there's an enormous body of literature in how to do search over large graphs. The classical thing that you would try to do is DepthFirst Search, right? DepthFirst Search has well-known problems. The biggest problem with DepthFirst Search is that it fails to find deep bugs, because it may, if your execution is, if your branching is very large, this is a very large state space, then you might just get stuck in some corner here, and you might not recover. Breadth-first search doesn't have this problem because it iteratively visits the states, but breadth-first search doesn't have that efficient implementation. The stack gives you a nice way of representing the frontier, right? In DepthFirst Search, you have to represent a queue, and that's not as compact. In P, because I know that concurrent systems and systems with failures in them can have huge amounts of branching. And that's the key value proposition, right? There's some value in being able to model things as an actor-style system. But I think if I just had that, people are not going to get so excited about P. So the main value proposition is really the systematic testing, which is treated as a search problem. So I better pay some attention to creating some value there, right? So the value that we are creating here is in search heuristics, search techniques of various sorts, both deterministic search, deterministic prioritized search, and random prioritized search. So I want to say a few words about that, and then I'll conclude. Okay? So let me explain what I mean by prioritization. So imagine that this is the space of all possibilities, executions, right? And this is the initial state. So what you're seeing by these onion rings is that the space has been partitioned into these increasingly large circles, right? These are the onion rings. So this is saying that you have a way of stratifying your search space. And the black circles represent one stratification strategy, and then the dotted blue circles or ovals represent another stratification strategy. In the limit, both strategies are guaranteed to explore everything, but if the time is limited, you have finite amount of resources, they will do different kinds of things, right? So this is the key. Because if there's a bug lurking over here, the black strategy reaches that in stratum number 5. The blue strategy reaches that in stratum number 2. If the size of each stratum is roughly the same, right, then it's better to do search with respect to the blue strategy, right, because you hit the bug early, right? So if you have these kinds of intuitions about various ways of prioritizing things, and you can feed them to the system in some way, then you let the system execute according to that strategy. That's what we're thinking about, right? So some of you might be familiar with the chess tool, and it had this hypothesis that bugs manifest in few context switches. That's an example of search prioritization. Here what we have done is that we have generalized that. So there's a general mechanism for telling the system what the prioritization function is. And all the system does is just executes that prioritized search. Nothing is baked in. Okay? So that is a little bit hard, because imagine that you have this concurrent system with this kind of bushiness, and you have two schedules. So here's a schedule A1, and that's a schedule A2. Well, how do you tell that I want to prioritize? How do you tell the system that I want to prioritize A1 over A2? Right? These schedules are not static objects. Right? They are emergent behavior of the system. Right? So what is, how do you tell the system, how do you tell the testing tool that do A1 before A2? Okay? So here is our one solution for it that we have designed. There's something called a delaying scheduler. Okay? So let me explain what a delaying scheduler is. It's a deterministic scheduler with a delay operation. Okay? Delay interpreted broadly. So here is an example of a deterministic round-robin scheduler. Supposing you have three processes, T1, T2, and T3. Then this is an execution in which T1, T2, and T3 are scheduled in a round-robin fashion. Right? So there's just one schedule possible. That's what a deterministic scheduler does. Right? A delaying deterministic scheduler has one other operation. It can choose to delay the next guy to be scheduled. So for example, if it executes the delay operation here, it will skip over T3, which was the next guy to be scheduled, and instead jumps to the one after that. So if for example, it might be easier to think in terms of the data structure used by the deterministic scheduler. The data structure just maintains a queue, right? And it just picks the first guy, the guy at the head of the queue, schedules it, and puts him at the back. Delay is very simple, right? He picks the guy at the front of the queue, puts him at the back, and doesn't schedule it. And then looks at the next one that's currently at the head. Okay? So that's a delay operation. Now, what you can do is you can use the delay operation to create a search prioritization. Because you can say that, okay, zero delay sphere is the set of all executions in which I did not do any delays. That's actually a set of cardinality 1. One delay is the set of all executions where I injected one delay, but you can do it wherever you want. Right? It's a bigger set. Then you can have 2 delays, then you can have 3 delays. So that's our mechanism for specifying a prioritization function. If you can choose whatever delaying deterministic scheduler you want. Whatever you pick creates a prioritization function. And the nice thing is that you specify the prioritization function basically as a program. You can put arbitrary amounts of computing power in the specification of this delaying scheduler. And it is fine, not a problem. So you can remember as much of the history as it wants. So that means you can really customize your search if you wanted to, if you had some intuition. OK, so that's one thing. So now you can just do prioritized search like this, basically how you would expect it. So you execute, you generate execution with 0 delay, then you pick various places to put a delay, then you generate executions with 1 delay, then you generate execution with 2 delays. So instead of thinking that you are doing a search over the transition graph of the system, you are really conducting a search over this imposed stratification graph, right? Where each node is an execution itself, is a full execution itself. And an execution is obtained from another execution by injecting a delay at a particular place in the execution. Okay. So another thing that we are investigating is the use of randomization, random sampling, to scale search. So a lot of the literature on searching state spaces is focused on deterministic techniques for searching. But random sampling has some advantages when these search spaces are very large. Well, one thing is that random sampling will not get stuck because every sample is independent of every other sample. So it can really try to divvy up the search over different parts of the state space, right? Very easy to implement. That's another huge advantage. Another advantage is that all the samples are independent. They don't depend on each other. There's no central data structure that's coordinating, like the queue or the stack, right, of pending work. So that means that it gives you a very efficient parallel implementation. So for a lot of these kinds of reasons, random sampling of executions, of concurrent executions, has received a lot of attention from the community, and for very good reasons, in my opinion. So here's how random sampling works. Basically, random walk, classic algorithm. I don't even know whom to attribute it to. So you start with the initial state. You have a bunch of outgoing transitions. Pick one randomly, flip a coin, right? Go to that one. Then again flip a coin and keep going like this, right? So this is just this algorithm. If you have complete control over the non-determinism, is just amazing, mind-blowing. That particular bug in PSharp, that one that I was talking about, the data loss bug, that was discovered using random walk. And the reason it works is because you have control over non-determinism. Something as simple as this, once you have control over non-determinism, is mind-blowingly effectively, more effective than stress testing. Again, the problem with random walk is that it's not prioritized, so you cannot direct the search towards one thing. But the prioritization mechanism that I was talking about with delaying schedulers, it works just fine with sampling also, because we have this overlaid graph of stratified executions, and you can do random sampling over that. Okay, so we have implemented all these things, and it works. Yeah.
When you do that, do you weight by the stratum so that the lower stratums have higher weight since you believe they're more likely to find bugs, or?
Well, no, you don't have to weight that. The weighting is already present in the definition of the prioritization function. That is already doing the biasing for you. Maybe there's another twist there that you can bias further. I mean, you have biased it already because you're going to look at these executions that are up here before you look at the executions down here, right? Okay, so I think that concludes the body of my talk. I have a couple more slides on things that we are pushing on right now, basically conclusions and future work. But I'll take questions now before I get into that. Yeah?
So do you guys do things like partial order reduction? Typical model vectors would do that?
No. So, well, yes and no. So In P, communication points are explicit, right? So it's only when you're sending a message or when you're creating a new machine. When you are doing internal computation inside a machine, accessing local fields, taking a transition from one state to another, that's all private communication. So you can call it partial order reduction, but it's kind of a folk theorem that you don't have to schedule other processes or other machines at those places. You only have to schedule other machines when you're doing a send. But there's nothing dynamic about it. It's just a static strategy. So partial order reduction is really about doing those kinds of optimizations dynamically as the search is unfolding. We don't do any of that. We don't do any of that.
Do you impose any sort of bounds on the size of data structures that can be used by the P program? The size of the queue of the...
No. Sometimes, there's that mechanism, but it's for the programmer. So for example, in a lot of embedded contexts, device drivers and so on, people actually want the queues to be bounded. And in fact, they would like that to be an assertion failure if the queue ever becomes larger. So then they can specify it, and then we will compile it. Yeah.
Instead of just like randomly picking executions, have you considered like looking at the program, maybe like symbolically executing it or something like that to see whether you can guide the search that way to places where the spec is violated?
Not yet, but it might be interesting. It might be interesting. I don't know how to do. What I want to say here?
You could use sort of like a symbolic evaluation to come up with a prioritization or something.
Yeah, maybe something.
It's like you can eliminate certain classes of things, where like the symbolic evaluation, like where it fails, that's where you wait.
So why is symbolic evaluation useful? I think that the reason it is useful is because it propagates the assertion that you are testing for, the property they're testing for backwards, right? Mm-hmm. So if you didn't do that, then you're basically reduced to enumerating the inputs one by one. And you don't really have a good way of picking one input over another. Symbolic execution at least gives you some kind of information backwards, right? So it is worth thinking about what are the sources of non-determinism here. So in this case, non-deterministic choice or non-determinism is coming from two places. It's coming from process non-determinism, scheduling non-determinism, and it's coming from that dollar, right? So very deliberately so far, I have stayed away from unbounded choice, or not unbounded, rather, right? Choice over non-Boolean choice.
Yeah.
Non-Boolean choice, I've stayed away from it, okay? So if you have only Boolean choice and you have scheduling choice, it is worth thinking about whether our classical intuitions about the value of symbolic execution still hold. I don't know. Maybe there's something to be investigated here. The other thing is that I can enhance my testing capabilities and even provide non-Boolean choice, non-Boolean non-deterministic choice, like choosing over all values of a particular type, int, or data types and so on and so forth. In that case, because that choice is so large, I think in that case we will have to use something like symbolic execution to pull back from the assertion. However, a symbolic execution-like techniques for concurrent programs, I think that's wide open. We don't really know how to do that well. But I think it's an interesting thing. Cheng, the guy who's working in Azure, VNext, that piece of software, he does want he's interested in that because sometimes, you have to pick a particular integer also in writing your unit test. And there is no help right now that the system gives about what integer to pick, right? You have to just scratch it, okay, maybe down here I'm doing some test here, so maybe I should use this integer. If you provided symbolic integers, for example, that might become a little bit more principled. Yeah. More questions?
We should thank the speaker. And then
Yeah.
if anybody, yeah. So.
And then I want to tell you about 2 things that I'm doing right now. So thank me, but don't leave.
Okay.
Okay, so I just wanted to tell you a little bit about what I'm currently, a couple things that I'm currently very excited about pushing on. So one of them is compositional reasoning. So in P, the program is written as a collection of state machines. So there's a little bit of code structuring there, but we don't really have any kind of modules in P. So we're not able to do our reasoning by breaking the program, P program, into pieces, right? So if you look at a large distributed system here, you have at the very bottom, the standard services that an OS provides, timer, network storage, and so on. And above that, you may build some consensus thing, right? And there are many options for building consensus. You can do Paxos, or you can do some chain replication family of protocols. These are both alternatives. And then above that, you can have higher level services like a two-phase commit, or you can have various sorts of distributed data structures. So as you can see, there's a family of protocols stacked one on top of each other. And wouldn't it be nice if we had a module structure in our programming language in which you can write down each piece separately and perhaps test each piece separately? Wouldn't that be nice, right? So that's something that I'm trying to do right now. Another thing is that this is more on the application side. We have a new cross-group collaborative effort on building a software stack for safer cyber-physical systems. And one of the specific CPS that we are interested in is drones. So we are actively working on using our improved and better programming techniques to make software better, safer in some way. And this is a relatively new effort, and kind of excited about that. And that's all. That's all I have to say.
Let's thank Shaz again.